everybody, it's Mrs. Hofferberth. Today we're going to be talking about how the structure of an acid relates to its strength. There are three primary factors that affect the strength of an acid. The bond polarity of the hydrogen to the rest of the acid molecule, the strength of that bond between hydrogen and the rest of the acid, and the stability of the conjugate base that forms. Let's start by talking about bond polarity. Remember that in a covalent molecule, the atoms are held together by the attraction between the nuclei and the shared electrons. But those electrons are not always shared equally. If the hydrogen and the atom to which it is attached in the acid, we'll call that one A, do not share the electrons equally, then you're going to see results in the strength of the acid. If the acid molecule, not the hydrogen, but the rest of whatever it's attached to, is attracting electrons towards itself, creating a polar bond, that leaves less electrons close to the hydrogen to be attracting the hydrogen itself, which makes it easier for the hydrogen to leave and results in a stronger acid. Thus, the more electronegative the acid atom that the hydrogen attaches to, the greater the polarity and the stronger the acid is going to be. Similarly, for bond strength, if you have a weaker bond, it's going to be easier to break it, and it's going to be easier for that hydrogen atom to leave, thus forming a stronger acid. The third piece of this, conjugate base stability, has to do with what you're making. If you make a product that is more stable, then you are going to end up with a greater likelihood that that product will form and will stick around, and thus you will end up with more products. If you look at this one from a potential energy diagram kind of standpoint, if you have two possible products, the more stable product will result in a greater accumulation of products, and thus the more stable your conjugate base is, the more that forward reaction will occur and the more products will accumulate, and the stronger your acid will be because you are making more of those dissociated products. As we look at how these play out in binary acids, it turns out that the defining feature depends on whether you're looking at the trend vertically within a group of acids or horizontally within acids as they change across a period as you change those elements. Within a group, bond strength wins. So if you look at bond strengths, I've got bond strengths down here for hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. And these are the HBr, HCl, HI, that bond strength. HF has a relatively strong bond, 567 kilojoules per mole, more than anything else. It's harder to break, you get fewer products, and that's going to be a weaker acid. On the contrary, if you get down to HI, you have a bond strength of only 229 kilojoules per mole. Much less energy is required to break that bond. You're going to get more products. These are going to be your stronger acids. And as you know, you actually have strong acids with HCl, HBr, and HI. If you're looking horizontally along a period, it turns out that electronegativity matters most. Things containing carbon and nitrogen, those are actually nonpolar bonds, and they don't act as acids, or bases for that matter. But if you go over here and you look, say, at the acids you would form with oxygen and fluorine, or the acids you would form with between sulfur and chlorine, so we've got H2O and HF. Fluorine is substantially more electronegative, and so as a result, there is less electron density shared with the hydrogen. It is going to be a stronger acid. So these get stronger as you go from left to right, but as you go towards the right and you have more electronegative atoms, you're going to get stronger acids. We see the same thing with H2S and HCl. HCl is substantially more electronegative than chlorine is, and so that is a stronger acid in hydrochloric acid than in hydrosulfuric acid, H2S. When you take a look at oxyacids, we need to first consider how these are put together. It turns out the hydrogen is actually bonded to an oxygen itself, which is then bonded to that other element, like the chlorine, the bromine, the sulfur, whatever it is. And to be generic, we're going to call that other element Y. And so when you look at it, this is your structure. And there can be extra things bonded to your chlorine or your bromine to your element Y, and that's going to matter. So when you look at this, first off, when you're looking at acid strength, the greater the electronegativity of that other central atom in your oxyacids, so the chlorine, the bromine, the sulfur, the more it's going to pull electron density towards itself away from the hydrogen, weakening the attraction to that hydrogen and making for a stronger acid. Similarly, if you start tossing extra oxygens onto your bromine, your chlorine, and so you're making something like HClO versus HClO2 versus HClO3, the more additional electronegative atoms you put in your conjugate base or in your acid that's going to turn into the conjugate base, the more you're drawing that electron density away from the hydrogen. Makes the hydrogen more likely to leave stronger acid. And the conjugate base that results with all those extra electronegative atoms is better able to stabilize the negative charge that the conjugate base has. That makes for a more stable conjugate base. And as we already talked about, that will also increase the strength of your acid. And so you're looking for the more electronegative element. So like for this one, chlorine's more electronegative, and so that will give a stronger acid for HClO. Or if you're looking within a series and you've got more electronegative elements bonded to that central atom, you're going to end up with a stronger acid. The last thing I want to talk about are carboxylic acids. These are a category of organic molecules, so they are carbon-based, that have acidic properties. And what makes these acidic is a particular arrangement of atoms that they all share that is called a carboxylic acid functional group. A functional group is just a particular arrangement of atoms, and this one's called a carboxylic acid. What makes a carboxylic acid acidic is that you have this hydrogen here that's bonded to the oxygen. Now, on the carbon, you have another electronegative oxygen. And so that's going to further pull electron density away from the oxygen-hydrogen bond, making that hydrogen easier to lose and increasing its acidity. If there are any other electronegative atoms in the vicinity, that will add to that. So that's one thing, is you have a nice polar bond. The second thing that you end up with impacting your acidity is the fact that your conjugate base is unusually stable. So if you look at the conjugate base that we form, we have now a negative charge on this oxygen, but this molecule has resonance forms. So it exhibits resonance, which means that those electrons are not localized on a single oxygen, but instead they are shared among both of the oxygens in that carboxylate functional group. The fact that you have this delocalization of electrons, where those electrons are spread amongst multiple atoms, that is stabilizing. And again, if you have a more stable conjugate base, that is going to lead to the forward reaction being favored, and you're going to have a stronger acid.